Very related to the slope of the tangent line and velocity is just the average rate of change. Velocity is just a rate of change. It's an instantaneous rate of change. It's just very specific because it's for position and velocity function. For position function and its velocity. But you can do rate of changes for any object. And so we can talk about the average rate of change, which again would be the slope, basically. So it'd be f of x2 minus x1 over x2 minus x1, or f of x1 plus h minus f of x1 over h, if you prefer the h notation. Instantaneous rate of change, therefore, would be that limit. You either let this change, delta x, go to 0. In other words, you let x2 go to x1, and you find the limit of that slope, or you do the limit as h goes to 0. They all mean the same thing. They all mean the exact same thing. We're letting h get really, really small. We're letting x1 get closer to x2 get closer to x1. We're letting delta x get really, really small. And this gives us this idea of this average rate of change and instantaneous rate of change. An example we would see this is, let's say we have a roast turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit. And it's placed on a table in a room where the temperature is 55 degrees Fahrenheit. So obviously the turkey will start to cool, and the question is how fast. The graph shows how the temperature of the turkey decreases and eventually approaches the room temperature. By measuring the slope of the tangent, we can estimate the rate of change of the temperature after an hour. So this is the equation, the graph that shows how that turkey is cooling down. It's actually known as Newton's law of cooling. And this slope here, this tangent line that I drew in here, is the slope of this tangent line is how fast it would be going at that point P. That P happens to be at 60 minutes, so we've been for 1 hour. So all we need to do is figure out what the slope of this line is, and then we can estimate. And this is just an estimate because we don't have any great equations here at the moment. We're just going to estimate what the value is. So one of the things I'm going to do is I'm going to find out what that is. So the thing you remember is your function here is, we'll call it that, we'll just call it, we don't need to call it anything, but if you want to, it's t of t. And all we have to do is find 2 points, and then we can find out what its change is. We're looking for the rate of change of t. And I know you don't like t of t because you think they're the same letter, but this is a capital T and this is a small t, and they are actually different in mathematics. All right, so we have to find the slope of that. And so to find the slope of any equation, just find 2 points. Since we actually have a line here, we can actually estimate those 2 points. So we can estimate this point here and estimate this point right here. Or we can use P. That might be a better estimate point. So it doesn't matter which point you use. They're all on the line, so they'll be fine. So P looks like the point 60. And then it looks like this is 100, 200, so that's 150. So it looks like about 125. And then this one looks like it's the point 30. The T is 30. And then it looks like it actually is right at the 150. So my rate of change of the temperature at a particular time is approximately equal to the difference in those. So 125 minus 150 over top of, since I used the 125 first, I got to use the 60 first minus the 30. So that's going to be 25 over negative 25, sorry, over 30. And so what I end up with is whatever that is equal to, and find that out really fast. So 25 divided by 30 is approximately, and you're fine leaving the answer that way, is approximately negative 0.08. I'm sorry, negative 8.3. The units of this, the top is in degrees Fahrenheit, the bottom is in minutes. So we have degrees Fahrenheit per minute. And there is the rate of change approximately. We know exactly what it is, but we can get an approximate answer from our graph. This concept of this rate of change is known as a derivative. So the derivative of a function out of number a is denoted by f prime of a. And its f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h, provided it exists. Or again, if you prefer x and a, you can use it as the limit as x approaches a of f of x minus f of a over x minus a. Either one, there's the same thing, just different ways of writing it. And so what we have here is we use this symbol f prime because it just gets too long to write out, as I did on this example, the rate of change. So this is just another way to write the rate of change. The derivative is just the rate of change, and we can find the derivative at any point. So let's find the derivative of this function at the point A. So that would be f prime at A of the limit as h goes to 0 of f of a plus h minus f of a all over h. So it helps you to know this formula and kind of memorize it. All right, so now we're going to go ahead and start doing this. Again, I'm going to start off with what my function is. So I have the limit. I haven't done that yet, so don't lose that symbol. I have my function, which is f times something squared minus 3 times something plus 2 minus my function of 5 times something squared minus 3 times something plus 2 all over h. And my something in the first case is a plus h. So I'm going to put an a plus h here. I'm going to have an a plus h here. My something in the second one is just a. So I'm going to put an a there and there. So if you forget what those are, just look at these parentheses here. Whatever's in this parenthesis goes in these. Whatever's in this parenthesis goes in here. That's your functional notation. Now we're just going to start doing algebra. So multiply this out. We got 5 times a squared plus 2ah plus h squared. Whoops. Minus 3a minus 3h plus 2 minus 5a squared plus 3a minus 2 all over h. Multiply your 5 through and then collect like terms. So you got 5a squared plus 10ah plus 5h squared minus 3a minus 3h plus 2 minus 5a squared plus 3a minus 2 all over h. Again, you're going to collect like terms. You got the 5a squared, the minus 5a squared, you got the 3a and the minus 3a, you got the 2 and the minus 2. So you've now collected your like terms. And I've got 10ah plus 5h squared minus 3h all over h. And then you notice every single term in the numerator has an h. Again, if that doesn't happen, you did something wrong. Mostly it's if you can't cancel this h in the bottom, you did something wrong. I can cancel that h in the bottom. I will cancel it out of each term, so it's going to be 10a plus 5h minus 3. And then, so this is what I started with, right? This is where I'm heading. And then I can now let h go to 0 because I no longer have the h in the bottom, and I can just use direct substitution. So I end up with 10a minus 3. And that is the derivative at a. That's the rate of change of this function. This was the function I was working with at a. Let's find the derivative of this one, of x, the square root of x. So again, that would be the derivative at 2, because we want at x equals 2. So that would be the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h equals the limit as h goes to 0, because I haven't done it yet. And then my function is the square root of something minus the square root of something all over h. In the first function, my something is 2 plus h. In the second something, my something is 2. So plug those in. And then I look at this and go, well, I don't know what to do with that. So this is where that concept of multiplying by the conjugate. We want to rationalize the numerator, which means we want to get radicals out of the numerator. So we're going to multiply by the conjugate of the numerator, which is 2 plus h plus the square root of 2. So all you do is between the two radicals, you change the sign. If it was minus, it's now plus. Remember, you got to do the same thing to the top and bottom, otherwise you're changing the function. So we have the limit as h goes to 0. Multiplying out the top, you've got the square root times itself, which is just the thing inside. You've got a square root times the square root of 2, positive, but then you're going to have a minus of that. So those are going to cancel. And then you got minus the 2 times the square root of 2 times 2. Square root of 2 is just 2. I would not multiply out the denominator. Again, you want to try to cancel this h out. If you multiply out the denominator, you just be factoring it back out. So let's just leave it in factored form. Now, go ahead and collect like terms. Notice the 2's cancel, and you're just left with h over h times the square root of 2 plus h plus the square root of 2. Now you notice this h can cancel. And again, if you're doing this right, you should be able to finally cancel that h. If you aren't doing it right, that h won't go away. Got 1 left in the top, square root of 2 plus h plus the square root of 2 in the bottom. Now you can take the limit. So this is actually the only calculus. The rest of this was all algebra. This is why I say algebra is the hard part. Calculus is easy because now the calculus is just letting h go to 0, which using the direct substitution property means you can just put 0 in for h. So you get 1 over the square root of 2 plus the square root of 2, or 1 over 2 square root of 2. And there's your derivative. Let's now find the equation of the tangent line to this point. So the equation of the tangent line, remember, is we're going to find this slope. The slope is m, the limit as h goes to 0, of f of 2 plus h in this case, minus f of 2, all over h. Well, notice this is just the derivative. The slope of the tangent line is the same as the derivative, so we're just finding the derivative of this function at 2. All right, so we're just finding the derivative. The slope of the tangent line is the exact same as the derivative. So now, again, we're going to do the limit as h goes to 0 of my function. My function is 5 times something squared minus 3 times something plus 2. Then I have that same function again, but I'm subtracting it. So 5 times something squared minus 3 times something plus 2 all over h. Now, the very first one is just 2 plus h. That's the something. The second something is just 2. Now we need to go ahead and multiply things out. I haven't done the limit, so don't lose that limit symbol. I'm going to have 5 times 2 squared, which is 4, plus 2 times 2, which is 4h, plus h squared, minus 3 times 2, which is 6. So minus 6, minus 3h plus 2. 2 squared is 4. 4 times 5 is minus 20. Plus 6 minus 2 all over h. So the limit as h goes to 0 of 20 plus 20h plus h squared minus 6 minus 3h plus 2 minus 20 plus 6 minus 2. Notice I didn't collect any like terms yet because I'm going to be canceling a bunch of things. So if I collected like terms, I'd just be canceling them again. So the 20s cancel, the 6s cancel, the 2s cancel. I now have the limit as h goes to 0 of 20h, and then I also have a 3h. So I actually have 17h because I have 20h minus 3h, which is 17h plus h squared. Everything else canceled over h. Cancel your h's in the bottom, which gives you 17 plus h. And then now let h go to 0. Constant goes to 17. h goes to 0, so it's just 0. So we now know that the slope of this tangent line is 17. So now we can do y minus y1 is equal to the slope. Now remember, y1 is your function evaluated at your a value. In this case, it happens to be 2. And then your slope is your derivative at 2 times x minus your a value, which in this case was 2. So we do need to find out what f of 2 is. So put 2 in for your function. F of 2 would be 2 squared is 4, 4 times 5 is 20. 2 times 3 is 6, so 20 minus 6 is 14, plus 2 is 16. So f of 2 is 16. So we've got y minus 16 is equal to 17 times x minus 2. So we have y minus 16 is equal to 17x minus 34. So y equals 17x minus 16 minus 34 minus 16. 14 minus 6 is 8. 2 minus 1 is so 18. And there's the equation of your tangent line.